Hello, today we're going to look at big idea number three, which is all about algorithms and programming. So first of all, what is algorithm? Algorithm is composed of a set of instructions, or we say steps, of solving a particular problem. It usually takes some kind of input and try to make some computation about the input as necessary, and then it's going to generate some desired output. So an example in our real life, if you would like to compare with algorithm, could be like a recipe. Let's say you want to cook some delicious dish, and then you're looking on the internet for recipes. When you look at the recipe, it will usually say things like, okay, you need these and these ingredients, and then you need to follow 1, 2, 3, 4, 5, all of those steps, and then follow the exact instructions, right, to create that dish. So algorithm is doing the same thing. So what you are trying to do is to create the recipe to solve a particular real world problem. And we can use many different languages to describe algorithms in computer science. They could be natural language, flowcharts, pseudocode, or the real programming languages. Let's first take a look at using natural language. Here's a very simple problem setting here. Uh, so step one, we're going to start the program, and then we're going to ask the user to type their name. If the user didn't type anything, we're going to ask again. So we're going to keep asking until the user really enters a non-empty name. So when a name is provided, we're just going to ask the program to display hello followed by the name that's entered by the user, and then end of program. So it's a very simple problem, right? To display what the user enters. We can also use a flow chart, which is basically a bunch of boxes representing, okay, here's a starting point and here's the ending point of this algorithm. After algorithm starts, it's going to ask the user to enter a name. And then if the name is entered, okay, if it's empty, it's going to go back here and ask the user to enter the name, keep entering the name. If it's not empty, right, if name is not empty is true, then we're going to print out hello, this particular name. And then we solve the problem and end the algorithm. So that's a flowchart representation of the same problem. We can also use pseudocode, which is pseudocode means it's close to a code, but it's not the real code. Okay, uh, it's just a way of describing the algorithm. So like in this pseudocode, it's basically like natural language, but it's in a more formatted way, and we're using specific terms and so on. So we're going to begin the algorithm, declare the name, this which is a variable that we're going to use to remember the name that's entered by the user. Okay, so we're going to simply say repeat this. Please enter your name. And then we're going to wait for the user to enter the name, input name. So we're going to repeat this until name is not empty. This double quotes here means it's not empty. So that means if the user enters something, then we're not going to repeat this anymore. And we're going to just output hello name and end the program. And finally, here is the actual programming language version. Here I'm using Python. We're going to start by, this is just a comment, right? Asking user. So we're going to initialize a variable name, which is empty. While the name is empty, we're just going to ask the user to enter your name. So, so this while loop will stop when name is not empty. So it will break out of the loop. And when the name is provided, simply print hello name and end the program. So that's also just a comment. All right, so let's take a look at the foundations of computer programming so you can start building your simple programs. So in a program, we definitely need variables. They are placeholders for values that can change over time. So it can be assigned a certain value at the beginning and change to a different value at different time to serve the purpose of the program. And variables can be of many different data types. It could be like a string, like our names, they're strings, right? Or it could be like an integer, numbers, or it could be a fractional numbers, like floating number, double numbers, or Boolean values. Boolean values are a special type that are either true or false. And variable names should be meaningful when you try to write the program. So, for example, like using count rather than just say I or J, um, so that when you read the program later on, you will understand what this particular variable is referring to. And variable names, they can be used to reference the data values. It can hold either a single data value or a collection of values, like it could be a list of values or an object of various different fields. So let's take a look at some of those fundamental data types. We're going to start with strings. So strings are text fields that are composed of series of characters, like what you're reading here. All of these are text fields. They are strings, characters, numbers, symbols. In APCSP, there are many pre-written functions that you can use for the string. It's pretty much like natural language. You're going to see functions such as concatenation, which is combining two strings into one string, concatenate one with another. And there's also a function called substring. And in APCSP, you can reference a character in string using its index. The first letter is always in index one. So for example, like in this character string, hi space Frank. Index one is letter H. Index two refers to I. Index three refers to the blank space, and so on. Okay, so you can see that this is a string of length 9. If I use substring, hi Frank, 1, 3, 1 basically means the starting index, okay, and 3 means the length. So it's going to return starting at index 1, length of 3, 1, 2, 3. So it's going to return this substring hi with a space in the end. Okay, so this is a lot different from many of the real coding, which usually starts at index 0. You just need to remember in APCSP, the first letter or the first number starts at 1 instead. So here's Python code where I'm going to create a string called name. Name equals to Alice. So for the string, usually we're using double quotes to represent it as a string. So we can simply print hello followed by the name, okay? And we can concatenate string. In the concatenation in Python works by just using the plus sign. Okay, so we can say hello, comma, space, the name, and then concatenate with the exclamation. So we're going to print greeting. Okay. And then the last one, we're going to try substring in Python. Substring in Python works a little bit different because it's the first index is the starting index and the last index is the ending index, not the length. Okay. But the end is exclusive. So let's run this code and see what's the result. So first of all, it's going to print hello, Alice. And then the second greeting will be a concatenation of hello plus Alice plus this exclamation. That's what's printed. And finally, for the substring, it works. It's going to take the start from the letter at the first index, which is E. Remember, it's starting for Python coding. Index 0 is the first letter. So this index 1, and then it's going to end at index 2. So this is index 2, but since it's exclusive, so it's just going to print out E. Okay, we can change to a different thing and see to 5. So this is printing out from 1, 2, 3, 4 because the ending index is exclusive. So in addition to strings, integers, fractions, they're also very popular in the program. So integers, they are like the whole numbers, like 1, 2, 3, 4, and so on, natural numbers, or it could be negative. Fractions, these are like numbers with decimal points, like 52.0. They could be either floats or doubles. So with numbers, we can do a lot of those mathematical kind of calculations, like all of those plus, minus, multiply, and divide, all of those operators. And then there's also a very special operator in computer science that is called mod. We use this percentage sign to represent mod, which returns the remainder. So here's how we calculate the result of mod. If we do 21 mod 4, we know that 4 times 5 is 20. So the remainder of this will be just 1. So 21 minus 20, that's 1. Since 21 equals to 5 times 4 plus 1. And then 3 mod 8 will just be 3, since 3 equals to 0 times 8 plus 3. So basically, we just need to write the number in this letter format so that we can find out the remainder. A very common use of mod is to find out whether a particular number is even or odd. So here's an example of telling whether the number is even or odd. So first of all, I'm asking the user to enter a number. Okay, and then I'm going to convert it into integer. And then if a number mod 2 equals to 0, that means it's the multiples of 2 because the remainder is always 0. So the number is even. Otherwise, it's 1. It's not even. It's odd. Okay, so let's enter a number, 8. 8 is even because 8 mod 2 is 0. And then round it again, 9 is odd because 9 mod 2 is 1. That's how you can use this mod operator to tell whether a number is even or odd. Let's take a look at some other examples like integers. So I'm going to define a variable a and b. They are 5 and 10. So I can do those arithmetic calculation to calculate the sum of a, b. These are still integers, but then I can calculate the average of those two. So the sum is still integer, but the average, it's a pointer number, right? It's decimal fraction numbers. And we can take a look at more of those modular function. Let's try out inputting a number, which is, let's say, 25. And then mod 5 should be 0, right? The quotient is 5. Try again. 5 mod 10 is 5 with a quotient of 0. 27 or 37 mod 11. So 37 equals to 33 plus 4. So the remainder is 4. That's the mod result. Boolean values, that's another type of interesting variable in a lot of the programming languages. We use that a lot with relational kind of operators, like to checking whether certain things equals to another thing or does not equal to, greater than, equal to, or less than equal to. Those are the relational operators. And we can also use them on logical operators like this and that, this or not something. Okay, so let's take a look at some examples. So we have these following integers defined. A is 5, B is 7. I'm going to print out value of A greater than B. Is A greater than B? No, right? So this is supposed to print out false. Is A less than B? 5 is less than 7. So this is supposed to print out true. And A does not equal to B, which is also true, right? So you can see the results. These are like the Boolean results from those relational operations. And we can use many different combinations to, like in a condition, to decide what to do. Okay. So for example, like we can define Boolean values. Sunny is true. Rainy is false. So that means, well, for today's weather, let's say it's sunny and it's not rainy. So before we do that, I just want to print out a bunch of those and or results. You can also do that yourself, like true and true. If A is true, B is true, the result of A and B will be true. So this is supposed to be true. True and false. A is true, but B is false. So the result will be false. True or false. If one of them is true, then it should be true. And let's take a look at that. right? True and true, the result is true. True and false, result is false, and so on. Okay, the negation of true is just false. Okay, so I'm going to use those conditions to help me decide whether I like to go outside. Um, I want to go outside if it's sunny and not rainy. Okay, so I'm going to print out, is it sunny? Is it rainy? False. So can we go outside? Yes. So the go outside is this and not is rainy. So it's like true and not false. So true and true, which is this particular case, which is true in the end. So once you know all of those fundamentals, we can definitely start writing programs. Actually, you have already seen a lot of those programs. For any program, it's interesting that it's just composed of some special type of those statements. There could be sequential statements. So those are the statements that are executed one after another. For those simple examples you just saw, they are just sequential statements. We execute one line after another in one particular order. But there could also be selections where different blocks of statements, they will be selected based upon the condition. Like we have a simple if case, right? For telling whether it's an odd number or even number. That one is a selection. And there could also be iterative statements where blocks of statements, they will be repeated based upon some predefined number or based upon some predefined conditions. So loops in APCSP, they are represented using those pseudocode. Like we're going to repeat for exactly n times, or we're going to repeat until certain condition is true or false. And we can also use a for each to loop through a particular list or array. And in Python, the equivalent for those will be using for loop or while loop. In this example, the user will be asked to enter a number. If the number is greater than 0, I'm going to execute this block, which is printing out the number is positive. Else means that it's less than equal to 0. So I'm going to print out the number is negative or 0. So let's say I'm going to enter -5. So it's only going to execute this second block. The number is negative or 0. Try again, 5. The number is positive, one block. So we're selecting which block of statements to execute, right? Here's like a extension of the if else. If I also want to separate the number 0, if it's greater than 0, then print out positive. If it's less than 0, I'm going to print out it's negative. Otherwise, else, I'm going to print out it's 0. So if I enter 0 now, it's going to print out the number is 0. All right. Here's a more complex example of assigning a letter grade based upon the score. So I'm going to ask the user, maybe it's a teacher, to enter the score. If the score is greater than equal to 90, the grade is set to be A. Else, ELIF, it means else if score is greater than equal to 80, I'm going to set it as B, and so on. And last, if none of those are true, I'm just going to set the grade to be F, okay, failure. Okay, so in the end, I'm going to print out the grade. So let's say I'm going to say 83. So that it's letter grade B. 77, C. 30, that's an F. So those are the selection blocks where we use the if-else statements. And as for looping condition, where I want certain things to execute for multiple times, I'm going to use for loop in Python. So here's how I'm going to declare a list of numbers. This list of numbers includes 2, 4, 6, 8. And I want to find out whether there are odd numbers in this list. So I'm going to initialize this is a Boolean value odds to be false. That means initially I do not know. So I need to check every single number. So I'm going to use this for loop for x in numbers. So this is going to start with index, the very first element in this list. Okay, and check if x mod 2 equals to 1. Remember, we use mod equals to 1 to represent it's an odd number. So if this is the case, then odd is true. Then we can simply break because there's odd number in that list. Okay. So if it's not an odd number, it's just going to go to the next element in the loop. Okay, so this for loop includes this block, whole block here. So it's going to go to the next element, mod it with 2, and keep checking until we have looked at every single number in this list. In the end, if odds is not set to be true, that means no odds found. But in any case, if there's any odd number in here, odds will be set to be true. So we're going to print out found and odd. So in this case, no odds found. Let me try to found and odd. Okay. So let's see what's the output of the following algorithm at 7 a.m. on Friday. So in this pseudocode, we say if it's Monday to Friday at 8 a.m., we're going to set the thermostat to 62. So is it 7 a.m.? No, not 7 a.m., right? The condition is not met there. Else, if it's Saturday or Sunday, I'm simply going to set it to be 70, which is also not the case. And then in the end, it doesn't matter which days. It just say if time is 5 p.m., so that means every day 5 p.m., I'm going to set the thermostat to 68. So none of the condition is 7 a.m. Friday, right? So what should be its temperature? It turns out that for 7 a.m. Friday, since none of the condition met, we're going to look at that O to see if it's Thursday night. After 5 p.m., the thermostat is going to be set to be 68 until it's going to change at 8 a.m. to 62. So that's why at 7 a.m. on Friday, the temperature is 68. Okay, so that's trying to use the if statement to understand this block of code. Here are more examples of using now the while loop. So in this case, we try to calculate an exponential number x to the n using a while loop. So I'm simply going to ask the user to enter the base and enter the exponent. So this exponent will be calculated by x times x times x for a total number of n times. So I'm going to start the result with 1, keep a count of how many times we have multiplied x. Okay, so while count is less than n, because n is the exponent, I'm just going to multiply the result with x. So first one will be 1 times x, so it will just be x. And then I'm going to increment the count. So in the end, count equals to n. This loop will not execute anymore. This block will not execute anymore, and then exit, right? So print out the result. I'm going to enter the base and enter the exponential number. So 32. Okay. So the equivalent pseudocode, if we write it in APCSP, will be going to ask the user to input x and n. We're going to set the result and count using repeat until. So this is repeating this until the condition is true. When this condition is true, I'm not going to execute this block, similar to this one. When count is n, this condition is false, I'm going to exit this while loop. All right, now let's take a look at some common data structures and algorithms that are used in APCSP. So what is data structure? Data structures, they are ways of organizing data so that data can be easily accessed, can be modified, can be added or removed. So one of such data structure we used in APCSP is called list. They are just a collection of the same elements that can be accessed by using an index, which always starts at 1 in APCSP. So why do we want to use a list? Let's say we have 10 data items, which they are of the same type that we want to keep. We want to use in the algorithm. Instead of creating 10 variables to store them, we can just create one list, which will contain such 10 elements. And then we can access those elements by index 1, 2, 3, 4, all the way to 10. Sometimes if we forgot about it and attempt to reference a position in the list that does not exist, your program will end up with an index out of bounds type of error. So like in the previous example, if we only have 10 elements in the array, but we try to access the 15th element in the array, then it's going to be indexed out of bounds. So for the list, there are some built-in methods that we can use in APCSP. They're called insert, append, remove, and length. And then we can use a loop for each loop or a while loop to go through the elements in the list. So let's take a look at some examples. So in this section, you're going to see some of those functionalities we just mentioned. So first of all, we use an empty bracket to represent an empty list. And then we use this arrow sign to assign that to a list name. We can also create a list that's initialized with value 1, value 2, and so on. To make a copy of a list, we just assign list 1 into list 2 to make that assignment. And we use this list name sub I to access the ith element in the list. So first element will be list name sub 1, second element will be list name sub 2, and so on. And the very last will be list name sub the length of this list. This insert function will insert a value at index I into this list. Append will basically append the value towards the end. Remove will remove the ith element from the list. And length of the list will simply return the number of elements in the list. And the for each loop will take the following format. We'll say for each item in this list, it will traverse through the list from the first element all the way to the very last element. It's going to execute the block of statements for each of the item. So let's take a look at this concrete example of finding the largest or the smallest number of a list. So here it's still pseudocode. So we're going to initialize the index to be 2, to be the second element in the list, and then the largest to be the very first element from the list. So we're going to repeat this block until we reach length plus 1. That means it's out of bounds. So we can exit, right? So for the block of code, if the current largest value is less than the current element in the list that the index is pointing to, then I'm going to update my largest to be the larger one. And then increment the index. So it will go to the next element. So when the first loop starts, it's going to compare the first element with the second element. Whichever is larger will be saved into largest. And then index will be increased. We're comparing the current largest with the third element and so on, all the way until length plus 1 is index. So let's take a look at the corresponding Python implementation for the largest number in the list. So we are going to initialize a list of 6 items and starting from index with 1. And the first element in this list, which is my list sub 0, will be stored in largest. So this block of code will continue running until length of this list equals to the index, which means, well, this will be index out of bound because the index actually in Python starts from 0 all the way to length minus 1. Okay, and whatever is inside here is the same as the pseudocode. So you can see that when we run this code, it's going to return the largest number, 25. Now let's take a look at this for each loop on the list. So we initialize the list again with 5 elements. We try to calculate the sum of numbers using for each loop. So we initialize total to be 0. And for each number in my list, I'm going to traverse through the list. I'm going to add that number to the sum total. Okay, so first I'm going to do 0 plus 3, and then 3 is saved in total. The next time it will be 3 plus 7, and keep going until the very last element. So you can see when we run this code, it's going to calculate the sum. And there are other interesting algorithms such as linear search versus binary search. So let's take a look at linear search first. Linear search means that we were given a list of numbers, which could be any random order, and we're also given a target we want to look for in this list. So linearly means that we're going to do it in a sequence, do the search in a sequence where we start from the very first element and then go all the way till the last element until we either find this element, we find the target, or we couldn't find it. We exhausted the whole list. So let's take a look at this linear search example where we initialized this list, my list, here with 6 values. They are, well, of random numbers. And we ask the user to randomly input a number that they want to search for. We set the flag to be false. Found is false. So for each number in the list, if that number is the target I'm looking for, I'm going to set found to be true and stop searching once the target is found. So break will basically break out of this loop, will stop the loop from continuing executing. Otherwise, if it's not the target we're looking for, it's going to look at the next element and then compare with target and keep going. In the end, if it's found, I'm going to print out number is found. Okay, let's try it out. So I'm going to input a number that's in there, which is 16. So number is found. Try it out on 22, number not found, right? It's just going through everything and return true. Going through the list in that particular order from the very beginning to the end or until the target is found. So comparing with a linear search, binary search is more interesting and also more efficient. So in a binary search, we can only apply that for sorted data. Sorted data basically means, for example, like numerical values, they're either sorted in a ascending order, meaning the next number is always greater than the current one. So it's in a increasing ascending order, or in a descending order from the largest to the smallest. So in this case, we have this list of numbers, and let's assume we are looking for value 6. Okay, so if we do a linear search when we're looking for value 6, then it's simply going to start from index 0. Compare with 5, it's not 6, so we're going to continue to 10, not 6, continue all the way until we reach 35 and find out 6 is not in this list. So in a binary search, instead of doing that, we're going to compare 6 with the middle element in this list, which is 20. Since this list is in order, 6 is less than 20. That means if 6 is in this list, it must be in this section, in the left section of 20. So the next time, we can discard the latter part. We don't need to search this part for 6 because apparently those values are greater than 20. We don't need to search 6. So it will reduce the list size to this first half only. So these arrow signs basically represent the starting point and the ending point, representing the portion of the list that I'm looking for this target. So in the second round, we're looking to compare 6 with this middle element again. It's smaller than 10, so that means it should be to the left of 10. So now we're just looking at the very first element of this list, and 5 is not 6. And then we're done with searching, means 6 is not in this list. So how many times are we doing comparison? We're doing it 1, 2, 3, 3 times. Instead of like in a linear search, we're comparing with every single element in this list. So binary search is more efficient. It's effectively cutting down the size of our search by half of the previous one. However, the caveat of that is that we can only apply binary search on a sorted list. Sometimes when we have more complex type of problem to be solved, we are going to create procedures or functions just to store those sections of code that will be executed many times when they are called. And we don't need to worry about the implementation details usually of those functions. We just need to know how to call those functions. So the good thing about organizing code using functions procedures is that we can reuse those functions and calls multiple times. We don't need to write it here and there everywhere in the program. We just need to write one function and then we can call that function multiple times. So that's reuse of code. It's easy to maintain. We only need to modify if so at one place, and the code is easier to read. And we say that is called modularities. So when we have functions, then we typically we will need to pass some values from the calling program to that function or procedure. These are called parameters. And then those values they passed are called arguments. So first of all, in terms of pseudocode, we will be using procedure, and this is representing, okay, it's a function, and followed by the procedure name, followed by parentheses with a bunch of parameters that we need for this particular function. So here's a Python example where we define this function to be greet. So greet is the procedure name, and name is the arguments that we pass. Name is the parameter that we want to receive an argument from the calling function. So in this function, we simply are going to print hello name. And when we call this function, we're going to use the procedure name followed by the argument we want to pass to that function. So you can see this is simply going to print out hello Alice and hello Bob. And here's another slightly more complex function with 2 parameters where we can calculate the rectangle area and return that value to the calling function. So A equals to rectangular area calculation, and A will store the value that's being returned here. Now, when we have lots of functions that we can use later on for other algorithms, they're usually called libraries. So libraries are those pre-written programs that provide those common functionalities that everyone can use. For example, like in this case, there's a library provides the random functionality, which is going to generate a random number between 1 and 10 in this case, and in an inclusive way. And a lot of time, we just have to deal with the API, which stands for Application Programming Interface, where we know how to use a particular library through those APIs, but we don't need to know the implementation details of them. So this is a nice way of hiding the implementation details while providing the functionalities to the users. So simulations are ways of mirroring the real world in order to test before the real application. It's a very high level of abstraction. So for example, before we try to test out the autopilot function on a helicopter, we might want to use the flight simulator to test it out first to see if all the functions they work fine. and under those different situations before we actually send out a real helicopter because it's really costly, right? And time consuming to test it out on the real helicopter and also dangerous if the function doesn't work, right? So when we use simulation or try to build simulation, we really need to watch for those biases because um, we're trying to do an abstraction of the real world, right? So obviously, we're going to leave a lot of those details of the worlds outside this simulator. So the choices of elements from the real environment will definitely influence our design. So with a simulation, we can definitely test out our functionalities, our hypothesis in a fast way, and be able to avoid those dangerous situations without putting anyone at risk. However, since our simulator leaves out a lot of those details of the world, it's not the 100% of replication of the real world. In the real world, there are lots of uncertainties and things that are varying. So many times in the simulation, we try to use a random number generator in order to simulate the randomness or the uncertainties in the world. So when we have lots of algorithms, how do we characterize them and say which algorithm is better? We can compare algorithms in terms of their efficiency. And in computer science, efficiency will be interpreted in terms of the time efficiency and space efficiency. So efficiency, they are defined in terms of the size of the input. For example, like if you see this figure on the right here, let's say if we have an algorithm that is of constant efficiency, that means no matter how we change the input size, the time or space efficiency remains constant. So that is a really nice algorithm because it's not, the computation time is not influenced by the size of the problem. A slightly worse one will be logarithm. Um, or linear. That means when we increase the size of our problem, the time also increases, but in a logarithm manner or in a linear manner. So a typical example we learned before that is of log n complexity is the binary search. And our linear search will be this linear complexity. Quadratic actually is also not that bad. It's one of the polynomial. So we will say constant, linear, quadratic, or even cubic, there are more reasonable efficiencies. But anything that goes beyond, like say n to the 10th, or exponential, like c to the n, or 2 to the n, they're called exponential. And even factorial, n factorial, those are unreasonable efficiencies. That means, well, the time quickly grows, right? Even with a small increase in the input size. So typically, the number of operations is just too large for the computer to complete. That's too complex of an algorithm. So algorithms, they also have limits, and sometimes it's very difficult to find the best solution. So in terms of finding the best, we try to find an estimation that's close to the best. So this is called heuristic. Say, for example, we can measure, let's say in Google Map, right, the distance between two cities. Maybe the real distance is um, too difficult to calculate, but we can use this estimation of straight line distance between 2 points to represent the estimation, which is as close, right? And there are also definitions of decidable and undecidable problems. So decidable problem is one where the algorithm can be written to produce an absolute yes or no answer for all kinds of inputs. While for undecidable problems, there's no such algorithm exists for all of the inputs. Maybe it exists for some inputs, but not for all. So that's the very famous halting problem in computer science, where given an arbitrary computer program with an arbitrary input, deciding whether it has an infinite loop. So this is undecidable. So these are some of the concepts that are commonly tested in APCSP regarding algorithms and programming. And in terms of writing programs, you actually need to do a lot of exercises to be good at it.